What's up, everybody? Welcome to a part 2 review for your general chemistry midterm exam. This review will cover every question that you will see on part 2. The only difference is that the numbers and the chemicals and atoms will be different, but all the skills are the same. So let's start with question number 1. Question 1, we have 741 grams of zinc, and we need to get to moles. So we're going to use our Triforce of Chemistry here. We're starting with moles. We want grams, so the relationship between moles and grams is that 1 mole is equal to the formula mass in grams. Grams will go on the bottom of my unit conversion so that the unit cancels out. Let's see how it works out here. So we have 741 grams. We put that over a plain old 1. Now we set up our conversion step. We have the unit grams on top, so we want unit grams on the bottom because that's what we're given. We want the unit moles at the end, so that goes on top. So 1 mole is equal to formula mass in grams. Formula mass of zinc is just zinc on the periodic table. Its mass is 65.41 grams. This causes the grams to cancel each other out. I multiply across my tops. I get 741 times 1 is 741, but my unit changed to moles. 1 times 65.41 is 65.41. Do the division. 741 divided by 65.41, I get 11.3. My unit is moles, and that is my answer. On to question number 2. It's another conversion question using the Triforce. This time, though, we're using the top end of the Triforce. Again, we want to get to moles at the center, but we are starting with cobalt atoms. All right, we have a big number of cobalt atoms, 3.45 times 10 to the 24th cobalt atoms. And the relationship between moles and atoms, 1 mole, is 6.022 times 10 to the 23rd atoms. But let's start by writing down what we were given and putting it over 1, 3.45 times 10 to the 24th atoms, all over a plain old 1. And now we can set up our conversion. All right, at the end of everything, we are going to want moles. And the relationship between moles and atoms, like I said a few minutes ago, is 6.022 times 10 to the 23rd atoms, or molecules if I had a compound, but here we have atoms. That goes on the bottom, so the atoms will eventually cross out. Moles, the unit I want, goes on top. It's always what I want over what I'm given. Multiply across the tops, I get 3.45 times 10 to the 24th times 1 mole, so that gives me 3.45 times 10 to the 24th moles. Multiply the bottoms, gives me 6.022 times 10 to the 23rd. I need to type this in a calculator. Remember, the way to do scientific notation on a calculator is use the EE button. The EE replaces the times 10. When I plug and chug this in the calculator, I get 5.73 moles. All the exponents end up canceling each other out. Question number 3, calculate the number of liters in 0.315 moles of carbon dioxide gas at STP, which is standard temperature and pressure. It is standard conditions. It's the only conditions we deal with. STP makes the right leg of the Triforce of Chemistry possible. There are 22.4 liters of a gas at STP in 1 mole. So we take what we're given, put it over 1. We're given 0.315 moles. Now we need to convert it. All right, what we want is going to go on top. What we're given's on the bottom. We're given moles, so we use 1 mole. We want liters, so we use 22.4 liters. The moles cancel. We take 0.315 times 22.4. The bottoms are all 1, so we just multiply those two. We get our answer at 7.06, and the unit is liters. And that is it. The last question on this page, the bottom half of the page here, we are looking at atomic structure things, and specifically of isotopes, which are atoms of the same element with different masses. One of the key things to remember about mass number, if we have mass and we subtract protons, we get neutrons. Also, remember that the atomic number is the number of protons, and in a balanced or neutral atom, which is what we are dealing with for all of these, it is also the number of electrons. So these 3 columns will be the same. In the first one, we're dealing with selenium 80, so we have to find selenium. Selenium element 34, 2 below oxygen in column 16. All right, well, its atomic number is 34. That means the protons are 34, the electrons are 34. This number after the name is the mass. That's how we can tell it's an isotope. We also put that number in the symbol. Selenium is Se, we put that 80 there. All right. We can go down to the next one and take a look. We have 34, we have selenium again, but we need to find the mass. Neutrons plus protons is the mass. 34 plus 43 is 77. On to the next one, we have selenium 74. So selenium, mass of 74. Our mass number 74. Because we have selenium, there are 34 protons and a 34 for the atomic number, which means there's 34 electrons. 74 minus 34 is 40. That ends up being a number of neutrons. The next row, atomic number 34 means 34 protons, 34 electrons. That means we have selenium once again. If I want the neutrons, it's mass minus protons, which is 48. Selenium symbol is Se. My mass this time is 82. Don't forget to put the mass number. The name of Se is selenium, and then we write the mass number of 82 to tell us what isotope it is. Second from bottom, 34 protons. Gives us the same number for atomic number and electrons. 76 minus 34 will give us 42 for our number of neutrons. Selenium is number 76, or selenium, mass of 76. Name, write the mass of 76. These are all the same thing. Here we go, atomic number 34. 34 protons, 34 electrons. Add protons and neutrons for mass, I get 78. Symbol is still Se. Name is still selenium, and don't forget to put those masses in there. Now I'm just realizing on that very first one, I never found the neutrons, so I gotta take 80 and subtract 34, and this gives me 46 neutrons. All right, so that is page 1. Here on page 2, we are either writing the chemical formula for different compound names or writing the names for different compound formulas. We are going to start with the writing of the formulas. We also have to determine if they're ionic or covalent. Remember, ionic compounds have metals in them, or they have parentheses from this common chart of polyatomic ions. Covalent compounds are not ionic, so they have no metals, and they also typically do not have parentheses. All right, so let's see what we've got here. Our first one is rubidium bromide. So we have to find rubidium. Periodic table. Look, it's shaded in. It's a metal. Right away, I know it's a metal. Rubidium has a charge of +1. Bromide ending in "ide", that means that it's probably an element unless it's hydroxide, but bromide is "ide". That means it's bromine. I picked the nonmetal that sounds like it. Bromine is Br-1. Cross the charges. The one goes to the bromine, the other one goes to the rubidium. I get Rb, Br. This is ionic. Rb is a metal. Keep in mind, watch your capital letters. Capital letters are more important in chemistry than any other subject. The second one, we have gold 1. Gold is Au. Notice it can be two charges, +1 and +3. This 1 means I have gold as +1. If there was a 3 after gold, it would be +3. Bromate ends in Ate. So it is not plain old Br. Ate and Ite means look at the back of the periodic table. Here's bromate right here, about the 7th one down. It is BrO3 in parentheses with a -1 charge. Crisscross the numbers from the charges. A 1 goes outside the parentheses. A 1 comes down to the gold. I just get Au BrO3. I can keep that BrO3 in parentheses, but I don't need them. It is also ionic because gold is a metal and BrO3 is a polyatomic ion in parentheses. Next, we have arsenic. Arsenic is As. It is a metalloid, not a metal. We also have pentachloride. Penta is a prefix. Penta is a prefix that means 5. Chloride, all right, means it comes from the nonmetal chlorine. So I write what I see here. 1 arsenic and 5 chlorine. So that's Cl5. There's no crisscross, no nothing, no metals, no parentheses. It is covalent. Fourth one, ammonium thiosulfate. Ammonium is special. It is the one very important positive polyatomic ion. There are others, but this is the one you'll see the most. Second down on the back of the table, it is NH4 in parentheses with a +1 charge. Thiosulfate, once again, we have that ATE ending. So we can find it on the back of the periodic table, very bottom. S2O3 in parentheses with a -2 charge. So what we have to do is we have to write down these symbols. Ammonium, NH4 with a +1 charge. Thiosulfate, S2O3 in parentheses with a -2 charge. Crisscross the numbers from the charges. The 1 is going to come down to thiosulfate. The 2 comes down to ammonium. So I get NH4 in parentheses with a 2, meaning I have 2 NH4s, and there's only 1 S2O3. There's a lot of parentheses, so even though there are no metals, we do have the or parentheses, so it's ionic. Finally, we have manganese 7 phosphate. Manganese, element 25, Mn. The Roman numeral 7 means that it is +7, which is a possible charge. Phosphate ends in ATE. It is down here. I forgot to highlight it. PO4 in parentheses with a -3 charge. Crisscross the numbers from the charges. All right, there's that highlighter on phosphate if you're still looking for it. This 7 comes to the outside of the phosphate parentheses, meaning I need 7 phosphates. I don't change the O4. I need 3 manganeses. So Mn3, PO4 in parentheses with a 7. Manganese is a metal. I see parentheses, so it is definitely ionic. Number 6 is going the other way. We now have the formulas. We need to write the names. All right, this should say compound name. NH4 in parentheses, I looked that up. It is ammonium. We just dealt with that. And PO4 is phosphate. We just had that a little while ago too. So I now write the name for PO4, which is phosphate. It's just ammonium phosphate. I'm dealing with polyatomic ions. Ions are ionic. We got Cr, C2O4 in parentheses. Cr is chromium. If I look, chromium can be +2, +3, or +6. I have to figure out which one it is. C2O4 in parentheses will help me figure that out. If I go and I look up C2O4 in parentheses, I'll find what that is second. So, like I said, Cr is chromium. I'm going to leave a little space because I'm going to need a Roman numeral. I have to be able to tell if it's chromium 2, chromium 3, or chromium 6. Oxalate is C2O4. It has a -2 charge. Well, there's only one oxalate. There's only one chromium. So the only way to get one of each is if they have the same charge. Since oxalate's -2, chromium must be +2, which means it gets a Roman numeral 2. Chromium is a metal. It's ionic. N2O3 is nitrogens and sulfurs, all nonmetals. It is covalent. That means I use prefixes. There are 2 nitrogens. The prefix for 2 is di. There are 3 sulfurs. The prefix for sulfur is tri. So I get dinitrogen for 2 nitrogen. Trisulfide. Remember, I still changed the ending to "ide" to make it sound pretty. K2CO3 in parentheses. K right here is potassium, has a +1 charge. CO3 is carbonate. Here it's getting highlighted in green. All right, -2 charge. Potassium only has 1 charge. I don't need a Roman numeral, so it's just named potassium for the K, carbonate for the CO3 in parentheses, and it is ionic. Again, parentheses and a metal. Finally, we got Fe2SO33. Reverse the crisscross to find out the charge of the Fe, because iron, Fe can be +2 or +3. I need to know which one I have, right? Because there are 3 SO3s, iron had to be +3. That means it's iron 3. SO3 in parentheses with a -2 charge is sulfite. So I get the name sulfite. Metal, polyatomic ion, we have an ionic compound. And that is it for page 2. Page 3 starts off with a question about finding a formula from a percent or grams. This is right from one of the reference sheets you'll get on the exam. So we have a compound that has strontium, 41.3%, chromium, 25.5%, and oxygen at 31.4%. based on their masses. So we have to determine the empirical formula, which is a formula in lowest terms. We are going to use these 3 steps from our reference sheet. And the first step is to convert to moles for each substance. Now, since we have percents, we can assume we have 100 grams, and that means that we can just change the percent sign right to a grams. So we're going to start with 43.1 grams of strontium. I got to convert this to moles. Well, according to the Triforce, 1 mole is equal to the formula mass in grams. Formula mass of strontium is on periodic table. It's 87.62 grams in 1 mole. The grams cancel each other out, and we get 43.1 moles divided by 87.62. Type it in a calculating device. and we get 0.492 moles of SR. But I have to do this for each part of the substance. That was just strontium, so now I got to do it for chromium. There are 25.5 grams of chromium. Well, it's the same conversion, just slightly different numbers. So we put it over 1, and we have the formula mass of chromium, which is 52.00 grams, causing my grams to cancel, are equal to 1 mole. So multiply my tops, 25.5 moles of chromium, over 1 times 52, which is just 52. Divide 25.5 divided by 52, and I find out I get 0.90 moles of Cr for chromium. Finally, I got to do the thing for oxygen, change that percent to a grams, write down my 31.4 grams of oxygen, put it over a 1 so I can establish a top and a bottom of a fraction, a numerator and a denominator, if you will. Now I got to convert this to moles. There are 16 grams of oxygen in 1 mole, causing those grams to cancel. This 16 is on the periodic table. 31.4 times 1 mole is 31.4 moles. 1 times 16 is 16. 31.4 moles of oxygen divided by 16 gives me 1.96 moles of oxygen. That was all step 1. In step 2, I now have to divide each of these mole amounts by the smallest mole amounts and then round to a whole number. Well, the smallest mole amount is 0.490. So I divide each of the 3 by 0.490 moles. For the SR, 0.492 divided by 0.490 comes out to 1 when I round as a whole number, so 1 strontium. 0.490 moles of chromium over 0.490 moles by moles, I get 1 Cr, 1 chromium. 1.96 moles of oxygen divided by 0.490 moles, rounded to a whole number, gives me 4 oxygens. These 1, 1, and 4, these are my subscripts. So I get an SR with a 1, a CR with a 1, and an O with a 4. That is the rewriting it as an empirical formula. Number 8 is going to ask us to find the molecular formula. The molecular formula is the real formula, the actual formula of the substance. All right, we can find that if we know something's empirical formula. Empirical formula is in lowest terms. So the lowest terms of this substance is C4H7O2. So there's going to be some multiple of this empirical formula as the real molecular formula. The real formula also has a formula mass, or a molecular mass, whatever you want to call it, of 261.29 grams per mole. So we know the mass of the total real formula. And we know what the lowest terms or empirical formula is. So to find out what the real formula is, we got to take that formula mass, which is going to be given to us right here, highlighted in purple, and we got to divide it by the mass of the empirical formula, called the empirical mass. That's not given to me, but the empirical formula is given to me. So I take that formula mass, 261.29, and now I have to find the empirical mass. My empirical mass will have 4 carbons, because there's 4 carbons, 7 hydrogens, because there's 7 hydrogens, and 2 oxygens, because there's 2 oxygens. And then I'm going to add these all up. So I take 4, and I multiply it by the mass of carbon, which is 12.01. It's on the periodic table. That gives me 48.04. I then need to take 7, multiply it by the atomic mass of hydrogen on my table, which is 1.008. That gives me 7.056. And then I need 2 oxygens. 2 times 16, according to my table. 2 times 16 is 32. I then add 48.04 plus 7.056 plus 32.00. And what I end up with is 87.096. That goes at the bottom here for my empirical mass. 261.29 divided by 87.096 gives me 3. So the real formula is 3 times larger than the empirical formula. So I multiply my empirical formula by 3, which means I distribute this 3 out to each element. 3 times 4 carbons is 12 carbons. 3 times 7 hydrogens is 21 hydrogens. 3 times 2 oxygens is 6 oxygens. And there's my answer. Question number 9 is a stoic question. But first, I got to balance the reaction. I have 1 copper before the arrow. I have 1 gold and 3 chlorines before the arrow. After the arrow, I have a copper. I have 2 chlorines, and I have 1 gold. Now, copper and gold look balanced, but chlorine is not. So if I double my AuCl3, that gives me 2 golds, 6 chlorines. I have to get to 6 chlorines. 6 or 2 times 3 is 6, so I put a 3 in front here. That gives me 3 coppers. That means I need a 3 in front of the copper. Because I have 2 golds now, I need a 2 in front of the gold. Now I have a balanced equation. The type of equation here is a single replacement or a single displacement. This is because I have a single element, copper, replacing gold, and I have a single element, gold, at the end. So it's single replacement because there is a single element on each side of the arrow. It's the only type of reaction like that. Now I get to the stoic part. I got 2 stoic questions here. The first stoic question is grams of copper metal. That is my given. I want to know how many grams of gold are going to be made at the end. So I write my given amount, my 15.0 grams of copper metal, just grams of copper, over 1. That's what I'm starting with. Number of grams of given chemical over 1. Now, I got to get to moles. 1 mole over the formula mass in grams. Formula mass of copper is just the mass of copper on my table, which is 63.55. This lets those grams get canceled. Now I get to the next step, the change the chemical step. I need to get rid of copper. So copper is going to go down here on the bottom. It has a 3 in my balanced equation, so it gets a 3 here. I want to go 2 gold, so the 2 golds go on top because there's a 2 before the gold. I've now canceled out the coppers. I have moles of gold. I don't want moles of gold. I want grams of gold. 1 mole on the bottom cancels out the moles, equals the formula mass of gold. According to my periodic table, the formula mass of gold is 196.97. Now I multiply my tops. 15 times 1 times 2 times 196.97, and I end up with 5,909.1 grams of gold, because grams and gold are not crossed out. 1 times 63.55 times 3 times 1 is 190.65. 5,909.1 divided by 190.65 gives me 31.0 grams of gold. Question D, I am now taking 15 grams of gold chloride, AuCl3, gold 3 chloride. And I want to know how many grams of gold are going to get to the end. So I have a different starting thing with the same ending thing. It's kind of like a limiting question. All right, my given amount in D is 15.0 grams of AuCl3. So I take my grams of AuCl3, I put it over a 1, I get a top and a bottom. First thing, change grams to moles. 1 mole on top is the formula mass in grams. My formula mass of AuCl3 is given to me right here in the question. It is 303.32 grams. Those grams cancel each other out. And now I can change my chemical. There are 2 AuCl3s in my balanced equation. They go on bottom, so they'll cancel. And there are 2 AUs. They go on top. All right, notice the grams canceled, the AuCl3s canceled. Now my final step, I got to get back to grams. 1 mole goes on the bottom to cancel out my moles. The formula mass of AU is 196.97. It's the same as it was here because AU is still AU. Multiply my tops, 15 times 1 times 2 times 196.97. I get 5,909.1 grams of gold. 1 times 303.32 times 2 times 1 gives me 606.64. 5,909.1 divided by 606.64 gives me 9.74 grams of gold. Now, if this was a limiting factor question, I would choose the smaller answer, which would be the 9.74 grams. And if I needed to figure out what limited this reaction, it's whatever produces the smaller answer. So the limiting here would be the AuCl3. Just in case this was a limiting factor question. This page is worth the most points of all of page or of all of part 2. So you might want to go through this page another time or two. Make sure you know how to do everything. Look for the 5 types of reactions from Unit 3. Look up your balancing from Unit 3. All right, and then C and D here, these are stoic questions of the Unit 6 that we probably just finished. Page 4 starts with an average atomic mass question. You will be given this formula on here. So we are going to find the average atomic mass of selenium to answer all these questions, or to answer this question, which uses this formula. So what we're really trying to find here is the average atomic mass. It's a weighted average of the masses of all the different isotopes. So we got to take mass of isotope times percent of isotope as a decimal. All right, and we do that for each of the isotopes. In this case, there are 6 isotopes. So for all 6, it's the mass times the percent as a decimal. So I got to take those percents, divide by 100 to get them as a decimal. 0.9 divided by 100 is 0.009. 9.4 divided by 100 is 0.094. 7.6 divided by 100 is 0.076. 24 over 100 is 0.24. 49.4 divided by 100 is 0.494. And 8.7 divided by 100 is 0.087. These are the percentages as decimals. This other column shows us the mass numbers. They are the numbers after the symbols. All right, so the first mass is 74, then 76, then 77, 78, 80, and 82. So it's these masses times these percents as a decimal. And then we add them all together to find the average atomic mass. So there are 1, 2, 3, 4, 5, 6 isotopes. So I got to do mass times percent as a decimal 6 times. The very first one is a mass of 74. I'm going to multiply that mass of 74 by 0.009, because that's the percent as a decimal. And that's really what I'm doing here. All right, I am then going to go do my next mass, which is 76. And so I take 76 and I multiply it by 0.094. And then to that I am going to add a mass of 77 times 0.076. Add to that a mass of 78. Times 0.24. Plus my mass of 80 times 0.494. And finally add to that my mass of 82 times 0.087. So now I'm going to go do the multiplication for each of these mass times percent as a decimal. All right, I get a handy calculating device, and I see that I have 0.67. And 76 times 0.094 is 7.14. 77 times 0.076 is 5.85. 78 times 0.24 is 18.72. 80 times 0.494 is 39.52. And 82 times 0.087 is 7.13. Now I add them all together, round to my 2 decimals, I get 79.03 atomic mass units, or AMU. The bottom half of this page is all that electron stuff that we did near the end of Unit 1. I have to do 3 things. I have to do abbreviated configuration, an orbital filling diagram, and a Lewis dot. First thing I got to do, though, is I got to find platinum. Here's platinum. And to do my abbreviated configuration, I have to jump up a row and go all the way to the end to find the noble gas. Because this is going to tell me that platinum contains every electron of xenon. All right, so I put it in brackets because those electrons won't go anywhere. And now I use the orbitals in parentheses and count the number of atoms until I get back to platinum. So I have a 6s orbital with 1, 2 atoms. Then I got to take a detour down to the F'ers at the bottom. And so I end up with the 4F group. All right, so there's 4F. And then I need to count across. And so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I get 4F with a 14. Now that I'm done with the F'ers, I jump back up to that big, thick D block in the middle of the table. It's 5D in this row. And I start counting 1, 2, 3, 4, 5, 6, 7. Platinum is the 8th one, so it gets 5D8. There's an abbreviated configuration. Part B, I need an orbital filling diagram. Now, this sounds like a lot of words. Orbital filling is not that hard. It's not that confusing. You might remember it a little better as the boxes and the arrows. Well, I got to remember how to do the boxes. Remember, the boxes go with these letters. Right? There's 4 letters we could have. We could have S, P, D, F, as in some people drink Fanta. And then we remember the sequence 1, 3, 5, 7, because that's how many boxes there are. So S has 1 box. P gets 3 boxes. D gets 5 boxes. And F gets 7 boxes. So starting out here, the first thing I have is the 6S. It's an S, so I get 1 box. I then come into the 4 Fs. Fs are frickin' big, so they get 7 boxes. And after the Fs are the Ds here, the 5D. D gets 5 boxes. Some people drink Fanta, 1, 3, 5, 7. In those boxes go arrows. The number of arrows are the exponents from my abbreviated electron configuration. So in the 6S box, I get 2 arrows. One's up, one's down. In the 4F box, I get 14 arrows. I half fill the boxes first because the electrons want to spread apart. And then when they're forced to team up, I put in the down arrows. So the up arrows were the first 7, and then 8 through 14 go and double up. For 5D, I got to put 8 arrows. The first 5 split up real nice, and then the last 3 start to team up. Right, and this is all happening in that 5D orbital. Finally, the Lewis dot diagram is I look at my number of S arrows and my number of P arrows, or my exponent on the S plus the exponent on the P. Notice there's no P here, so there's no exponent. All right, so this is all about figuring out how many dots there are. It is S and P only. All right, or I can look at my S arrows and my P arrows. I have no P arrows. S arrows are 2. No P arrows is 0. 2 plus 0 is 2. I put 2 dots around the symbol. Page 5 is first of 2 lab-based questions. We did a lab just like this, but with magnesium instead of barium. And so we have a data table, and we're going to use that to answer all the questions. So upon looking at the data table, we have the mass of an empty crucible and lid. I'm going to call this mass A. We then have a mass of a crucible, a lid, and barium. So we added some barium. This is going to be mass B. And then we have a mass of a crucible, a lid, and barium oxide. This is what happens after we've heated that barium high enough to react with the oxygen in the air, and this will be mass C. So the first question at looking at this lab is to find the mass of barium used. So we're going to take our mass of crucible, lid, and barium, and we're going to subtract the crucible and the lid. So that's B minus A. What's going to be left is just the barium. B is 37.35. A is 32.23. And if I subtract these two, I end up with 5.12 grams. So that's how much barium I used. The second question is the mass of the barium oxide. Well, it's a very similar question to answer. I got a crucible, a lid, and barium oxide as mass C. I have the crucible and lid as mass A, so I'm just going to take the crucible and lid away from the barium oxide. So I take the 37.88 grams of the crucible, lid, and barium oxide, and I subtract the 32.23 grams of the just crucible and lid, and that leaves me with 5.65 grams of barium oxide. Next, I'm trying to find the percentage of barium in barium oxide. I'm going to use my percent composition equation. All right, this is on your reference sheet. I'm going to take the mass of the part, which is barium, over the mass of the whole thing, which is barium oxide. So I wanted to find the amount of barium in barium oxide from the experiment. Well, the amount of barium is what I discovered and calculated in part A. So this 5.12 grams is my mass of barium used. So that's what goes on top. The 5.65 grams is the mass of barium oxide that was produced. Barium oxide is the whole thing. That is going on the bottom. So I end up with 90.6% of this substance is barium. 5.12 over 5.65 times 100 gives me a percent. Now, the real formula for barium oxide is BaO. So I need to take the mass of Ba and divide it by the formula mass of BaO. I can find all of this on my periodic table. The mass of barium ends up being 137.33. Right from the periodic table. Barium is in the second column. It is second from the bottom. BaO is the mass of barium, 137.33, plus the mass of oxygen, which is 16.00. That gives me 153.33. I now divide 137.33 divided by 153.33, and then multiply by 100, and I get 89.6%. So I have an experimental percentage, what I would say the percentage was from the experiment itself, and I have the theoretical value, which is what I would determine based on the formula and using math itself. So the experimental value, my answer to number C, is going to go in right in the equation here for experimental value. My theoretical value is my answer for D. It is going to go into the two spots marked theoretical value. So for the top part, I'm taking the absolute value. That just gets rid of negative signs. But I'm take the absolute value of the experimental value, 90.6, minus the theoretical value, that is 89.6. You gotta subtract those. And then after I subtract those, I'm going to take that answer and divide the whole thing by the 89.6, because that is the theoretical value. That's what I should get if everything went perfect. 90.6 minus 89.6 gives me 1.0. 89.6 is still 89.6. 1 divided by 89.6 times 100 gives me 1.12%. And that is going 2% from an experimental or an empirical formula and the data. And finally, we come to the last page and the last question, which is another lab question based on a hydrate. So we have a mass of an empty test tube. I'm going to call that mass A for this question. We have a mass of a test tube with the hydrate. That'll be mass B. And then a mass of a test tube with the anhydrous. Anhydrous means the no water, anti-water version, mass C. All right, so the amount of hydrate I used is just that mass B minus mass A. I'm just subtracting out the mass of the test tube. So 19.21 minus 14.76. This gives me 4.45 grams. That's how much hydrate I used. All right, we did a lab with a blue crystal and got rid of the blue. This might be a different color. The mass of the anhydrous, after all the color was gone, we take mass C, 17.62, and we subtract mass A, which is just the test tube, which is 14.76. So we have 2.86 grams as my mass of my anhydrous. Now the difference between the anhydrous and the hydrate is the water that was lost. So I take that mass of the hydrate, which had water in it, 4.45, and I subtract the mass of the anhydrous, which is what was left when the water was gone, 2.86. The difference between these two is how much water escaped or was lost or was liberated, however you want to call it. 4.45 minus 2.86 is 1.52 grams. So this is my amount of water that was lost from the hydrate. Based on these results, I need to find a percent composition of water or the hydrate. My mass of my part is going to be my mass of water lost. The mass of the whole thing is going to be the mass of the hydrate, because originally there was water in the hydrate, so I want to know what the percentage of water from the hydrate was. And then I multiply by that sweet 100 to get a percent. The mass of the water was my answer to C, 1.52 grams. My mass of my hydrate was my answer to A, 4.45 grams. The grams end up canceling. If I take 1.52, divide it by 4.45, multiply by 100, I get 34.2%. That is the percentage of water my data is telling me the hydrate had. Part E is using the hydrate's actual formula, which is MgBr2 stupid dot 6 H2Os. That means there's 6 waters trapped for every magnesium bromide. So to find my percent of water in this, I need the mass of the water. So there are 6 waters in this hydrate. So I need the mass of 6 waters. That is the part. It's the mass of the 6 waters. I need to divide that by the mass of the whole thing. Mass of the whole thing is the mass of the magnesium bromide, the MgBr2, plus the mass of the 6 waters. That's why this dot is stupid. Do not multiply. The dot doesn't mean multiply. It means those waters are trapped. So we're adding 6 waters to it. Now, my formula mass of water is given to me in the question here. It is 18.02. So at the top of this fraction, I have 6 times 18.02. On the bottom of my fraction, my mass of MgBr2 is given to me in the question, 184.11, plus, don't forget that addition, plus I have to add mass of 6 waters, because there are 6 waters that we are starting out with. So that's plus 6 times 18.02. Again, I'm going to multiply by 100 at the end to get my percent. 6 times 18.02 is 108.12. So that's what goes on top. 108.12 is what goes in for the 6 18.02s on the bottom. 184.11 plus 108.12 gives me 292.23. Then I multiply by 100. 108.12 divided by 292.23 times 100 gives me 37.0%. This is how much water I should have gotten out of my hydrate. I didn't get that much out, but that's why it's a lab. So let's figure out my percent error. It's the same percent error question as we did on the last page, except this time D right here is my experimental value. 34.2 is my experimental value. My answer to E is my theoretical value, which was 37.0. So I'm now going to plug these two values into the equation. So my experimental value is the absolute value of 34.2, which is my experimental value. It tells me it is right here, all right? Minus 37.0, which was my theoretical value. That's all going to be divided by 37.0, and then I'll multiply by 100. When I do the subtraction, I get 34.2 minus 37. This gives me negative 2.8, and divide that by 37. First, I take the absolute value, gets rid of the negative sign. So I need 2.8 divided by 37.0 times 100. So this equals 2.8 over 37. I get 7.57%. So that is the percent error from this experiment, which means it's not too bad of an experiment. That is the entirety of part 2 of the exam. If you've seen something on here that you didn't get, you're gonna see it again on the exam, I guarantee it. So maybe try to watch it again. Maybe reach out to your teacher and ask a question. A lot of possible things you can do. Ask a friend. Figure out what it's asking about, what the question is asking. Search YouTube. Find somebody that's not me to explain it. But I guarantee you it is on the exam. So thank you very much. Have a good night.